Hi, it's Mr. Anderson, and this is Chemistry Essentials Video 66. It's on Le Chatelier's principle, also referred to as equilibrium law, and it's a really elegant principle that you apply to reversible reactions. And it basically says if there's ever a disturbance to equilibrium, the reaction will move to counteract that disturbance. And so let's say, for example, I'm at an equilibrium state between reactants and products, and I all of a sudden get an influx of reactants, way more reactants. It's going to throw my equilibrium out. And so what can I do? Well, since this is a reversible reaction, I can move the reaction from the left to the right according to Le Chatelier's principle. And as I do that, I increase the amount of products and I bring it back into balance. That's essentially Le Chatelier's principle. And so according to that, in any reversible reaction where we have reactants and products and it's established in equilibrium, if we ever have a disturbance, and that disturbance could be adding or removing chemicals, it could be a decrease in volume, an increase in pressure, it could be an increase in temperature, a decrease in temperature, or even dilution, what's going to happen is a new equilibrium is going to be reestablished again. And so let me give you an example of that, a graphical example. If we're looking at the Haber process where we're taking nitrogen and hydrogen gas and converting it into ammonia, this could be our initial equilibrium, where we have given amounts of concentration of each of these. But let's say at this point right here, there's an influx of hydrogen. So we're increasing the amount of hydrogen. So that means we're increasing the reactants on the left side of the reaction. According to Le Chatelier's principle, the reaction simply moves to counteract that additional reactants. And so which way is it going to move? It's going to move to the right. And so what's going to happen to the amount of hydrogen? It's going to decrease. What's going to happen to the amount of ammonia? It's going to increase. What's going to happen to the amount of nitrogen? It's going to decrease because it's a reactant as well. And so a new equilibrium is going to be established. And so if we look at this at the molecular level, so this is all of our gases. Again, they're all mixed in together, but we have varying amounts of that. Let's say we get an increase in the amount of hydrogen gas. How can we get rid of that hydrogen gas? We can simply combine it with nitrogen, make more ammonia, and then we can reestablish that new equilibrium again. This also applies to pressure caused by changes in volume as well. And so let's say we're looking at this reversible reaction where we have dinitrogen tetraoxide, which is a clear gas, which can move reversibly to nitrogen dioxide, which is going to be a reddish brown gas. And let's say we put a mixture of these gases at equilibrium inside this chamber right here, and I were to simply decrease the volume. So if I decrease the volume, it's going to be more concentrated, and so we're going to have a darker color. But if you were to watch it for a given amount of time, it'll turn back to that color. And so it's important that we understand really what's going on, and you can't figure it out looking at it this way. Let's look at it at the molecular level. So originally, we had a mixture of those gases that look like that. And why was it reddish, brownish? Because we had enough of those nitrogen dioxides, which are going to be these ones right here, which give it that kind of a color. So what happens when I squeeze it? What happens when I decrease the volume? I'm increasing the pressure of those gases. And so according to Le Chatelier's principle, what's it going to do? It's going to move to counteract that increased pressure. Well, how can it do that? Well, if you look here at the reaction, we've got 2 moles of the nitrogen dioxide on the right side, but only 1 mole on the left side. And so if we could move this reaction from the right to the left, we can decrease the number of moles that we have, and we can alleviate some of that pressure. And that's really what's going on. And it's going to take a little bit of time for that to occur, but that reaction is switching from the right back to the left. This also applies to temperature and energy as well. So let's look at that same reaction. Again, we're taking this colorless dinitrogen tetraoxide and moving it into nitrogen dioxide, which is reddish brown. As we move from the left to the right side, that's going to be an endothermic reaction. What does that mean? It actually takes in heat from the surroundings as we move from the left to the right side. And so I'm simply going to add that heat down on the left side, and we can now treat it as a reactant. And so what happens if we increase the temperature? If we increase the temperature, if we increase that heat, what it's really doing is it's essentially adding more reactants. It's adding more things on the left side. And remember when we added more hydrogen in that Haber process, what happened? It switched to the right side. So we had a shift towards the right side. What's that going to do? It's going to push our reaction to the right. We're going to get a darker color. And so this is the same concentration of gas, but here and here they've heated it up. And so we're seeing that reaction move to the right side to counteract that increased temperatures. Likewise, what happens if we decrease the temperature? It's like decreasing the reactants on the left side, and now it's going to move towards the left side, and we're going to have more of that colorless gas. And so Le Chatelier's principle is wonderful, and we can apply it, for example, to increase yield. And so let's say we're looking at this Haber process where we have nitrogen gas and hydrogen gas making ammonia. This is an exothermic reaction, and so that means we could put heat on the right side. And so let's say I want to increase the amount of ammonia. Well, let's look at the concentration. If I want to increase the amount of ammonia, what would I do? I would simply increase the reactants. If I can increase the concentration of my reactants, it's going to push the reaction to the right side. I'm going to have more of that ammonia. Let's look at the next one. How could I increase my percent yield by changing the volume and thereby the pressure? Well, if you look on the left side, we have if we look on the left side, we have 4 moles. On the right side, we have 2 moles. And so if I could squeeze this reaction, it's going to convert towards lower moles. It's going to convert towards that ammonia. I'm going to have a greater percent yield as well. Now let's look at temperature. I mean, the temptation is to say just heat it up, and that's going to give us more of the yield. But since this is an exothermic reaction, that means we have more heat on the right side. And so if I increase the temperature, it's actually going to push it back to the left side. And so I would want to decrease this reaction's temperature in order to get more of that percent yield. In actuality, there's a nice balance because we want it to go quickly, and so temperature and pressure are actually balanced out. And so did you learn which way the reaction is going to shift based on disturbances, be it either concentration or pressure or temperature? And then finally, could you, given a reaction, figure out ways by changing temperature, volume, and concentration to increase percent yield? I hope so, and I hope this was helpful.